So, welcome to the second session on problem solving for trigonometric and inverse trigonometric functions. So, just like the previous session, we will solve some challenging problems involving the identities that we have learned and discussed for both inverse trigonometric and trigonometric functions. So, this is going to be the last lecture on trigonometric and inverse trigonometric functions. So, this is the first problem. So, what we have here is that we have angle theta which must lie between minus pi by 6 and minus pi by 12, and it says that suppose alpha 1 and beta 1 are the roots of this quadratic equation and alpha 2 and beta 2 are the roots of the second quadratic equation, which is this one. And it said that if alpha 1 is greater than beta 1, so alpha 1 is the larger of the two roots of this quadratic equation, and alpha 2 is the larger of the two roots of this second quadratic equation. So, it is asking us to find the value of alpha 1 plus beta 2. So, we start off with the first quadratic equation, which is x square minus 2x secant theta plus 1 equals 0. So, the two roots are alpha 1 and beta 1. So, the two roots are so we get two roots, one with the plus sign, the other one is with the minus sign here, and some simplification will give us sec theta plus minus square root of sec square theta minus 1. And then of course, we use the identity that for any theta, sec square theta is 1 plus tan square theta. So, the two roots are sec theta plus minus tan theta, and then because secant theta is 1 over cos theta, we can also write this as 1 plus minus sin theta over cos theta. Now, alpha 1, so we have been asked to find the value of alpha 1 plus beta 2, and it said that alpha 1 is the larger of the two roots of the first quadratic equation. So, we need to find out which one of the two is the larger one out of the two roots here. Now, since theta, we know that theta belongs to the interval minus pi by 6. So, it is actually an open interval minus pi by 6 to minus pi over 12, and when theta is in this range, we know that sin theta is negative, and therefore, out of the two roots here, the larger root is the one with the minus sign, and hence alpha 1, which is the larger root, is equal to 1 minus sin theta over cos theta. And of course, the other fact that we have used here is that cos theta is positive. So, because when theta belongs to this interval, cos theta is positive, and therefore, the denominator here is positive, but since sin theta is negative, the larger root out of these two, which is alpha 1, is going to be 1 minus sin theta over cos theta. And then we take the second equation. So, the second equation was x square plus 2x tan theta 2x tan theta minus 1 equals 0. So, the two roots of this equation are alpha 2 and beta 2, which are equal to minus 2 tan theta plus minus square root of 4 tan square theta plus 4 over 2, which is equal to minus tan theta plus minus square root of 1 plus tan square theta. And then of course, here we use the identity that 1 plus tan square theta is in fact sec square theta. So, we are going to use this identity here, and then it follows that the two roots of the second quadratic equation are minus tan theta plus minus secant theta, which is plus minus 1 minus sin theta over cos theta. Now, again, since theta belongs to the open interval minus pi by 6 to minus pi over 12, it follows that sin theta is negative and cos theta is positive. Now, the two roots here are, so the first root is 1 minus sin theta over cos theta, and the other root is minus 1 minus sin theta over cos theta. So, we know that cos theta is positive, and we have a minus sin theta for both the roots, but then for this root we have a minus 1 here, and then we have a plus 1 for the other root, and therefore, it is clear that for theta belonging to this interval, since cos theta is positive, this root is greater than the other root. And therefore, since it was said that out of alpha 2 and beta 2, it was said that alpha 2 is the greater root. So, the greater root is denoted by alpha 2 and the smaller root is beta 2. And if you also see, what we have been asked for is to calculate the value of alpha 1 plus beta 2. So, we are interested in finding the expression for beta 2, which is the smaller of the two roots of this quadratic equation. So, since this is the smaller root, it is clear that this is equal to beta 2, and then we just need to add alpha 1 and beta 2. So, if you remember, alpha 1 was this value. So, from the previous slide, we have alpha 1 equal to 1 minus sin theta over cos theta, which is from the first slide. And therefore, if we add alpha 1 to beta 2, what we get is, so this gets added to this. So, the 1 over cos theta is going to get cancelled, and at the end what we get is minus of 2 tan theta. So, the final answer is that alpha 1 plus beta 2 equals minus 2 tan theta, equals minus 2 tan theta. You take up the second problem now. So, this is the second problem. We are asked to find the number of possible values of theta such that theta lies in the open interval 0 to pi, for which this system of equations has a solution. But if you see here, we have theta as one of the variables, then the other variables are x, y and z, and the question is asking us that this system of equations, so there are three equations, has a solution x naught, y naught, z naught with y naught, z naught not equal to 0. So, with y naught times z naught not equal to 0. The first equation was y plus z times cos 3 theta equals x, y, z times sine of 3 theta. And then in the second equation, we multiply both the left and the right hand side with y times z, because y times z is, we know that it is not, so we are looking for a solution where y times z is not equal to 0, and that is why if we will multiply y times z on both the sides of this equation, and when we do that, what we get is x, y, z sine of 3 theta is equal to 2z cos of 3 theta plus 2y sine of 3 theta, sine of 3 theta. And then of course, we have the last equation, which is x y z into sine 3 theta equals y plus 2z times cos 3 theta plus y times sine 3 theta. So, in all these three equations, what we see is that, so this is common to all the three equations. So, essentially what we have is two equations, and so the two equations are as follows. So, the first equation is y plus z into cos 3 theta equals, so this obviously has to be equal to this, which is 2z cos 3 theta plus 2y sine 3 theta. And then the second equation that we have is that this quantity here should be also equal to y plus z into cos 3 theta. So y plus z into cos 3 theta is also equal to y plus 2z into cos 3 theta plus y sine 3 theta. So, if we see for a given theta, what we have is essentially a system of two equations and two unknowns y and z. The solution set should be such that the y z, neither should y be equal to 0 nor should z be equal to 0. What we see from both these equations is that ultimately these right hand sides have to be equal, and the right hand side here can be written as y cos 3 theta and then plus 2z cos 3 theta plus y sine 3 theta. So, if we see 2z cos 3 theta is also here. So, since this entire right hand side has to be also equal to the right hand side here, because both of them are equal to the same quantity, which is y plus z into cos 3 theta. So, eventually what we get is that 2z cos 3 theta plus 2y sine 3 theta equals y cos 3 theta plus 2z cos 3 theta plus y sine 3 theta. Of course, this and this term get cancelled, and then what remains is that y sine 3 theta is equal to y cos 3 theta, which can be written as y into sine 3 theta minus cos 3 theta equals 0. Now, since we are looking for a solution to this, so we are looking for such a solution such that neither should y be equal to 0 nor should z be equal to 0, because it was mentioned in the question that the solution should be such that the product of y and z is not 0. So, if the product of two numbers is not 0, it basically means that neither of the two numbers is 0. So, since y cannot be equal to 0, from this statement it follows that sine 3 theta minus cos 3 theta has to be equal to 0. So, that has to be satisfied. Since y is not equal to 0, from this equation it follows that sine 3 theta minus cos 3 theta should be equal to 0, or essentially that sine 3 theta should be equal to cos 3 theta. So, now if we go back and if we use this fact in the first equation here, what we get is that y plus z into cos 3 theta equals 2z plus 2y, because Sin 3 theta and cos 3 theta are the same. So, we can write it as 2z plus 2y times cos 3 theta. So, essentially what we have now is that these two equations are equivalent to these set of two equations. Of course, we are using the fact that the solution set is such that y is not equal to 0 and neither is z. Now, from the first equation here, what we will end up getting is that we can write sin 3 theta minus cos 3 theta equal to 0 as, so this left hand side can be written as is the same as 1 by root 2 sin 3 theta minus 1 by root 2 cos 3 theta equals 0, and this can then be written as sin 3 theta into cos pi over 4, because cos pi over 4 is 1 over root 2 minus sin pi over 4 into cos 3 theta equals 0. But this is of the form sin A cos B minus sin A cos B minus cos A sin B. So, this is sin of A minus B, which is sin of 3 theta minus pi over 4 equals 0. So, we have used the sin of A minus B formula here with A equal to 3 theta and B equal to pi by 4. And then the solution to this trigonometric equation, as we all know, is that 3 theta minus pi by 4 should be equal to n pi for some integer n, which essentially implies that theta is of the form n pi over 3 plus pi over 12 for some integer n. But remember that it was mentioned that theta has to belong to the open interval 0 to pi, and therefore, the three possible solutions are theta equal to, since theta has to belong to 0 to pi, we can only choose n to be 0, 1 and 2. So, with n equal to 0, we get the solution pi by 12. With n equal to 1, we get the solution as pi by 3 plus pi by 12, which is actually 5 pi over 12. With n equal to 2, we get 2 pi by 3 plus pi over 12, which is 3 pi over 4. So, these are the three possible values of theta for which the set of given solutions to this equation are such that y is not equal to 0. But we still need to go back and test this other equation. But what we see here is that whenever theta is taking either of these three values, we know that cos 3 theta is not equal to 0. So, and the only way then that this equation is satisfied is that y plus z is equal to 0, because from this equation we can write that. So, from this equation we can write that y plus z into cos of 3 theta equals 0. But since cos of 3 theta for any of these angles is not 0, so since cos 3 theta is not 0, the only other option is that y plus z is 0. But in any case, we have already answered the question, because the answer to this question is that the number of possible values of theta for which the system of equation has a solution where y times z is not 0 is 3, because there are three solutions: pi by 12, 5 pi by 12 and 3 pi over 4. So, that finishes the solution to the second problem also. We now take up another interesting problem, and we have been asked to find the number of distinct solutions to this trigonometric equation. So, initially when we look at it, we might get a little disturbed by looking at the sixth power of sine and cosine and the fourth power. But another thing that should be observed and can be seen is that we do have, whenever we have sine, we also have cos with the same power. So, sine 6x and cos 6x. Similarly, sine to the power 4 and then cos to the power 4 also. So, that suggests that one possible way is to use the fact that sine square x plus cos square x equals 1, and then take the cube of this equation, and then from that try to find out an expression for sine 6x plus cos 6x. So, we will first do that. Since we know that sine square x plus cos square x is 1, if we take the cube, then this is also true, and then we use the formula for a plus b cube, which gives us on the left hand side with a equal to sine square x and b equal to cos square x. So, if you recollect, a plus b cube equals a cube plus b cube plus 3 a b square plus 3 a square b. So, if we use this formula here with a equal to sine square x and b equal to cos square x, what we get on the left hand side is sine 6x plus cos 6x. So, these two are the terms which are actually present here, and then we get the remaining terms. So, we get plus 3 times sine square x into cos 4x plus 3 times cos square x into sine 4x, and this is equal to 1. And therefore, if we take these two terms on the right hand side, what we will get is that sine 6x plus cos 6x equals 1 minus 3 sine square x cos 4x minus 3 cos square x sine 4x. So, we have this little identity so far. In a similar manner, we can also find an expression for sine 4x plus cos 4x. So, instead of performing the cube, we have to square. So, sine square x plus cos square x has to be squared. So, this is also equal to 1, and then if we use the a plus b square formula, what we get is sine 4x plus cos 4x plus 2 sine square x cos square x is 1, and therefore, from here it is clear that sine 4x plus cos 4x equals 1 minus 2 sine square x cos square x. And then of course, the other term was 5 by 4 times cos square of 2x. But we know that cos of 2x is equal to cos square x minus sine square x, and therefore, cos square of 2x will be cos 4x plus sine 4x minus 2 sine square x cos square x. So, we now are going to use all these three identities that we have derived. So, we will replace all these three by their corresponding right hand side. So, now I am going to write an expression for the entire left hand side here in this equation. So, the first thing is 5 by 4 times cos square of 2x. So, for cos square of 2x, I am going to use this right hand side expression. So, it will be 5 by 4 times instead of, so we are not going to, so let us not use this right hand side, let us just keep it as cos square of 2x at the moment. So, we still keep it as cos square of 2x, and then we have cos 4x, sin 4x, cos 6x and sin 6x. So, from the previous slide we know that sin 4x plus cos 4x is this value. So, instead of sin 4x plus cos 4x, we are going to use the value 1 minus 2 sin square x cos square x, and then for sin 6x plus cos 6x we are going to use this right hand side, which is 1 minus 3 sin square x cos 4x minus 3 cos square x sin 4x, and it is given in the question that this entire, we need to find an x such that this whole left hand side is equal to 2. So, this 2 obviously gets cancelled with this 1 and 1 here, and then what we end up getting is, and we can further combine these two terms, because so the left hand side becomes minus 2. So, we can take all these three terms on the right hand side. So, 2 sin square x cos square x, and then these two terms we can take as common sin square x into cos square x times sin square x plus cos square x. So, this comes from these two terms taken on the right hand side, and of course, sin square x plus cos square x is equal to 1. So, this gets simplified to 5 times sin square x cos square x. So, we finally end up with 5 by 4 cos square 2x is equal to this, which is the same as writing that cos square 2x equals 4 sin square x cos square x, which is equal to 2 sin x cos x whole square, but 2 sin x cos x is the same as sine of 2x. So, this becomes equal to sine square of 2x. So, x must satisfy this equation. So, we have cos square 2x is equal to sine square 2x, and that can be then be written as cos square 2x minus sine square 2x is 0. But then we see that this is nothing but cos of 4x, because here we use the cos 2 theta formula. So, we know that cos 2 theta is cos square theta minus sine square theta. So, with theta equal to 2x, this is what we get. So, from here it follows that cos 4x is 0, and so if we go back to the question, we were asked to find all the values of x, or the number of distinct values of x which are in the interval 0 to 2 pi, which are solutions to this trigonometric equation. So, the solution to this equation, in the general solution, is that 4x is of the form. So, this 4x has to basically be a odd multiple of pi by 2. So, I can write it as 2n plus 1 times pi by 2, where n is an integer, and from here it follows that x has to be of the form. So, x is basically an odd multiple of pi by 8, and we also need to find only those. So, this is the general solution. So, we can take n to be any integer, we will get infinitely many different solutions to the trigonometric equation, but we are only interested in those solutions which lie in the closed interval 0 to 2 pi. So, obviously, those solutions are x equal to, so we start with, so we cannot take n equal to minus 1, because then x becomes negative. So, we have to start with n equal to 0. So, with n equal to 0, the first solution is pi by 8, and then with n equal to 1, the second solution is 3 pi by 8, n equal to 2, we have 5 pi by 8 and then 7 pi by 8 followed by, so all the odd multiples of pi by 8, 11 pi by 8, 13 pi by 8, 15 pi by 8, but we can't go beyond because the next is 17 pi by 8 and 17 pi by 8 is more than 2 pi. So, this is not allowed, and if you see all of these solutions are distinct. So, therefore, the answer to this question is that there are 8 distinct solutions of this equation in the interval 0 to 2 pi. So, these are the 8 1, 2, 3, 4, 5, 6, 7 and 8. So, the next question is here. So, it is asking us to prove that the values taken by this particular ratio of trigonometric functions does not lie between 1 by 3 and 3 for any real value of x that we might take. So, starting off, we immediately realize that this is nothing but because we see sin x and cos x. So, sin x over cos x is tan x, and then in the denominator we have sin 3x and cos 3x in the numerator. So, this entire thing is essentially equal to tan x by tan 3x. And here we will have to use the formula of tan 3x in terms of tan x. So, if we remember, the formula was for any angle x, tan of 3x is 3 tan x minus tan cube x over 1 minus 3 tan square x. So, if we use this right hand side over here, this ratio becomes equal to 1 minus 3 tan square x over 3 minus tan square x. Now, we know that tan x takes all values between minus infinity and plus infinity, and therefore, tan square x will be taking all values between 0 to infinity. So, tan square x will be a non-negative real number. So, then what we will do is we will represent this as 1 minus 3a over 3 minus a, where a is defined as tan square x, and of course, we know that a is greater than equal to 0. So, a could be any, depending on x, a could take any value between 0 to infinity. So, a essentially belongs to 0 to infinity. So, what the question is asking us to prove is that for we have to show that for a belonging to the interval. So, for a belonging to the interval 0 to infinity, we have to show that this ratio 1 minus 3a over 3 minus a, it never takes any value between. So, this value will never belong to the interval 1 by 3 to 3. So, it says it does not lie between 1 by 3 and 3. So, this is essentially what we have to prove. Now, we start off with, so this is what we have, and that can be written as 9 minus 3a minus 8 over 3 minus a, and this 9 minus 3a is 3 times the denominator. So, this is equal to 3 minus 8 over 3 minus a. So, at this point we have to divide we have to treat two different set of values that a can take. A of course is non-negative. So, we first consider all those values of a which belong to the interval between 0 to 3. Of course, we will not because at a equal to 3 this is not defined. So, that is why we have an open interval here. So, for a greater than or equal to 0 and strictly less than 3, so for when a belongs to this interval, it is easy to see that 3 minus a is, so the denominator here which is 3 minus a is greater than 0, and also that since a is greater than 0, it also follows that 3 minus a has to be less than or equal to 3. So, this is what is true. Or this could even be written as a minus 3 is greater than or equal to minus 3 and is negative. That is one and the same thing. And then if we, so now we need to find, well, this can also be written as 3 plus 8 over a minus 3. And then we need to find the range of values for 8 over a minus 3. So, it is clear that since a minus 3 is greater than minus 3, it is clear that 8 over a minus 3, because so essentially we are going to use this particular inequality here, and we know that a minus 3 is negative when a belongs to this range. So, obviously 8 over a minus 3 is bounded from below by minus infinity. So, that is obviously correct, that it is greater than minus infinity, that is coming from this particular inequality in the on the previous line. And then we also have that this is, so this is less than or equal to from this one here minus 8 by 3. So, if we use this inequality here, what we, so we just have to add 3 to all the, so to 3 to everywhere in this inequality, and therefore, if we add 3 everywhere in this inequality, so we add 3 here, we add a 3 here, and we add a 3 here. So, the final inequality after that we get is so then, so this is exactly this quantity. So, at the end what we get is that if a belongs to the interval 0 to 3, then this particular ratio which is this will take all values which are less than or equal to, and if you calculate this, this is 1 over 3. So, when a belongs to 0 to 3, then 1 minus 3 a over 3 minus a belongs to minus infinity to 1 over 3. So, this is the set to which 1 minus 3 a over 3 minus a belongs to. So, let me summarize that. So, what we have shown on the previous slide is that if a belongs to 0 to 3, then 1 minus 3 a over 3 minus a belongs to minus infinity to 1 over 3. And then of course, we take the second case. So, if a belongs to 3 to infinity, which means that a is greater than 3, it cannot be equal to 3. So, in that case again what we see is that, so if you remember, we had 1 minus 3 a over 3 minus a to be equal to 3 plus 8 over a minus 3. and we have that. So, from here it follows that since a is greater than 3, this implies that a minus 3 is greater than 0, and therefore, this quantity here is always positive. So, this quantity here is always positive, and hence this particular value here is always larger than 3. So, for this region, we therefore what we get is that 1 minus 3 a over 3 minus a belongs to, so we will take the values 3 to infinity, and that is because this thing is positive. So, from here what if we use this equality, then what we get is that 8 by a minus 3 is strictly greater than 0, and it is also less than infinity. And then if we add 3 on all the sides, we add 3 everywhere, then we will get this thing. So, hence what we have shown is that by taking these two, by considering these two cases together, we see that the values taken by this fraction are either below 1 by 3, or they are greater than 3, and hence this shows that this fraction 1 minus 3 upon 3 minus a will never take any value which is between 1 by 3 and 3. So, that finishes the proof of the fourth question, and now we take up the last question of this session. So, we are asked to find the value of, so the value of this summation, which is 13 terms. The kth term is 1 over sine pi over 4 plus k minus 1 pi over 6 times sine pi over 4 plus k pi over 6. So, this reminds us of the sin A sin B formula. We know that 2 sin A sin B is equal to cos of A minus B minus cos of A plus B. So, that is what we are going to use here with this entire thing as A and this as B. And then if we do that, well, but we also need a factor of 2 here. So, we multiply both the numerator and the denominator by 2, and then this denominator is simply equal to cos A minus B. So, cos of A minus B is going to be cos of pi over 6, and then minus cos of A plus B. So, cos of A plus B will be pi by 2 plus 2 k minus 1 times pi over 6. And we know that cos of 90 plus theta, so cos of 90 degrees plus theta is minus sin theta. So, we know that for any theta, cos of pi by 2 plus theta is minus sin theta. So, if we use this fact here, the kth term of this summation is equal to cos pi by 6 plus sine of 2 k minus 1 times pi over 6. And therefore, this entire summation simply becomes summation k equal to 1 to 13 2 over. Now, cos of pi by 6, we know that cos of pi by 6 is nothing but square root of 3 over 2. So, we write that here directly, and then plus sine of 2 k minus 1 times pi over 6. Another thing that we realize by looking at this term is that if we look at the kth term, so this is the kth term, let us look at the k plus 6th term. So, the k plus 6th term in the summation is going to be sine of 2 into, instead of k we have to write k plus 6 minus 1 into pi over 6, which is equal to sine of 2 k minus 1 times pi plus 12 pi. So, So, this over 6 plus 12 pi over 6, which is equal to sine of 2k minus 1 pi over 6 plus 2 pi. But sine of 2 pi plus some angle is the sine is equal to the sine of the angle itself. So, this is equal to therefore sine of 2k minus 1 pi over 6, which is nothing but the kth term. So, we realize that the kth term and the k plus 6th term are indeed the same, and therefore, it follows that the first and the 7th term are the same, the second and the 8th term are the same. So, we can add both of them together. So, what we can do is we can rewrite this entire summation as summation k equal to 1 to 6, because if we see the first and the 7th term are together. By what I mean by together is that they are equal, and then the second and the 8th term are equal, the third and the 9th term are equal, the 4th and the 10th are equal, the 5th and the 11th are equal, and the 6th and the 12th terms are equal, and the 13th term has to be treated separately. So, essentially if we have to add all these first 12 terms, it only suffices to add the first 6 terms, to add just the first 6 terms and multiply that sum by a factor of 2, because the 7th term is the same as the first term, the 8th is also the same as the second. So, adding all the 12 terms is equivalent to just adding the first 6 terms and multiplying the sum by a factor of 2. So, then the entire summation of the 13 terms becomes equal to, so the double of the kth term is going to be 4 over root 3 over 2 plus sine of 2k minus 1 pi over 6. And then of course, we have a remaining 13th term which still remains, because since the 13th term is left out, we need to write another term here, which is 2 over root 3 over 2 plus sine of. So, when we put k equal to 13, we get sine of 25 pi by 6. So, we get sine of 25 pi by 6, which is equal to sine of 4 pi plus pi by 6. But sine of 4 pi plus pi by 6 is the same as sine of pi by 6, because the sine function is periodic with integer multiples of 2 pi. So, this is our the last term. So, now we have to basically calculate the sum of these 6 terms. So, that is what our goal is. So, we can just write down all of these 6 terms now. So, the kth term is 4 upon root 3 by 2 plus sine of 2k minus 1 times pi over 6. So, we will write all the 4 terms now. So, we will write all the 6 terms now. So, with k equal to 1, the first term is 4 divided by square root of 3 over 2 plus sine of pi by 6, and then the second term is 4 over square root of 3 over 2 plus sine of 3 pi by 6. When you put k equal to 2 here, you get sine of 3 pi by 6, but sine of 3 pi by 6 is sine of pi by 2, which is exactly equal to 1. K equal to 3, we get 4 over square root of 3 over 2 plus sine of 5 pi by 6. But sine of 5 pi by 6, sine of 5 pi by 6 is the same as sine of pi over 6, and sine of pi by 6 is exactly equal to half. So, if we want, we can even replace this by half here, and this is also half. And then for k equal to 4, we get 4 over square root of 3 over 2 plus sine of 7 pi by 6, and sine of 7 pi by 6 is equal to minus half. So, we will write minus half here. K equal to 5, we get 4 divided by root 3 over 2, and then when we put 5 here we get 9 pi by 6. Sine of 9 pi by 6 is sine of 9 minus sine of 9 pi by 6 is sine of 3 pi by 2, which is minus 1. And then the last and the sixth term is, so when we put 6 here we get 11 pi by 6. So, sine of 11 pi by 6 is the same as minus half, because sine of 11 pi by 6 is equal to minus of sine of pi by 6. So, this is minus half. So, we just need to add all of this now, and a simple algebra will show that, and it is a little bit of an exercise left for you, is that if you add all of these 6 terms you will get the sum to be 0. So, essentially what then happens is that this entire big summation goes to 0, and therefore, this is the final answer. So, the final answer is 2 over square root of 3 over 2 plus half, which is 4 divided by square root of 3 plus 1. And if I multiply both the numerator and denominator by square root of 3 minus 1, then what I get is 4 into square root of 3 minus 1, and in the denominator I get 2, which gets cancelled with the numerator. So, the final answer is 2 times square root of 3 minus 1. So, that finishes the last problem also, and with that we finish the second problem solving session. From the next lecture onwards, we are going to start discussion on properties of triangles. Thank you.